In this video, we are going to see about the error detection techniques in data link layer in computer networks course. These are few references. In error detection, we first focus on the types of errors we can have. Single bit error or burst error. So if the sent data word is received incorrectly and in the incorrect data only one bit is changed, only one bit is corrupted, then that is called as single bit error. Otherwise we can call it as burst error. If we have multiple bits that are changed randomly here and there, that is called as burst error. Continuously 2 bits are changed means we can say multi-bit error. So in that way also we can represent something. So now if 011 is sent but 001 is received, then the type of error would be, so we could see how many bits are changed. So first bit and the third bit are as it is, the center bit is changed. So only one bit is changed, single bit error. If 01001 is sent but 0010111 is received, then this type of error we could see there is a change in second bit, third bit, fourth, fifth, sixth, seventh and eighth are same. So then we could call it as multi-bit error. Then in this case, first bit is okay, second bit is changed, third is okay, fourth is okay, fifth is okay, but sixth is changed. 7 and 8 are okay. So we could call it as burst error. In block coding, we divide our message into blocks. Each of k bits called data words. And each of k plus r bits, we are calling it as code word. That means r redundant bits will be added. So the length will be equal to n. So that is the size of the code word. So the extra r bits are mainly added for error detection purposes. So how do we choose this extra r bits? How do we calculate it? So in block coding, if the number of redundant bits is 3 and the number of data word bits is 4, then what is the size of the code word? So if we add these two, we'll get the size of the code word. So here it is 4 plus 3, 7. And we have a set of data words, each of size k, and set of code words, each of size n. Then with k bits, we can create a combination of 2 power k data words, and with n bits, we can create a combination of 2 power n code words. Since n is greater than k, the possible number of code words is larger than the number of possible data words. So some code words are not used because we should preserve one-to-one mapping. One data word and the corresponding code word. Then only the receiver can accept it. So these many code words are invalid. So now in block coding, if the number of code word bits is 5 and the number of data word bits is 4, then how many invalid code words are there? So how do we calculate this? 2 power 4 data words are there. 2 power 5 code words are there. When we subtract these two, we'll get 16 code words that are invalid. Now, let us assume k value, size of data word is 2 and n value, size of code word is 3. So we have list of data words and code words. Assume The sender encodes the data word 01 as 011 and the receiver receives it as 011. Is it valid? Yes. So the receiver don't know what is the data word. So he simply checks whether the received code word is available here. Yes, it is available. So the receiver accepts it. Now, for the same case, the receiver receives it as 111 instead of 011. The receiver receives it as 111. Receiver checks with the list of valid code words. 111 is not at all available here. So simply he tells this is an invalid code word. Some error has happened. He simply rejects the incoming data. Then for the same case, if the sender sends 011 but the receiver receives it as 000, is it valid? So the receiver only checks with the set of valid code words. So 000 is available in the valid code word set. So erroneously, the receiver assumes that the corresponding data word is 00. So if two bits are changed, you could see here, second bit is changed, third bit is changed. Okay, if two bits are changed, we cannot detect it. So the error detecting code what we have designed can detect only the types of error for which it is designed. Other types of errors may remain undetected. So in the previous case, it is designed only for single bit error. So multi-bit error cannot be detected. Hamming distance. Hamming distance between two data words of same size is the number of differences between the corresponding bits. Two, not data words, two code words. Okay. So distance between the two code words. So using this, we can identify whether there is some error or not. So this is one important value in error detection. So the received code word and sent code word are checked. How many number of bits are modified? So that size is Hamming distance. If Hamming distance is a non-zero value, there are some errors. If it is 0, that means all bits are same as sent. Then we can say there is no error in the received code word. So if the code word is 000000, but originally received is 01101. So how many bits are changed? Second bit there is a change, third bit there is a change, and fifth bit there is a change. So totally 3 bits are in error. So Hamming distance would be 3. In other words, we could say the value is a non-zero value. So the code word has been corrupted during the transmission. Hamming distance can also be found if we apply XOR operation on the two valid code words and count the number of ones in the result. Not two valid code words, sent code word and the received code word. So we can apply like this. So if we apply XOR operation, we'll get like this. Different bits are there, the result will be 1 in XOR. So 3 ones are there. So 3 bits are corrupted. Now calculate the Hamming distance for this 000 and 011. So Hamming distance would be how many number of bits that are changed between these two pairs. So 2 bits are different. So the Hamming distance would be 2. Now for this, how do we calculate the Hamming distance? First bit is same, second bit is changed, third is same, fourth is changed, fifth is also changed. So the Hamming distance would be 3. Now minimum Hamming distance. In a set of code words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs of code words. So we have to calculate it. So in a coding scheme that has Hamming distance, minimum Hamming distance, dmin, that is equal to 4 means This code guarantees the detection of up to 3 errors. If dmin is 4, then we can detect up to S errors. S D minus 1 errors. So S value here is 3. So S plus 1. So if I want to detect up to 4-bit errors means my code's minimum hamming distance would be 5. So in that way we have to define that. Find the minimum hamming distance of the coding scheme given in the table. So we have to calculate the distance between 1 and 2, distance between 1 and 3, distance between 1 and 4, then 2 and 3, 2 and 4, and then these two. So these many hamming distances we have to calculate, and among that which is minimum. So that will be the minimum hamming distance. So all hamming distance are calculated, all are equal to, so the minimum hamming distance is also 2. Now, minimum hamming distance for this coding scheme. So, similar way, distance between these two, distance between these two, distance between these two, and distance between these two, distance between these two, and these two. So, we have to calculate. Finally, we have to derive the minimum hamming distance. So some are having 4, some are having 3. So the minimum hamming distance here is 3 for this coding scheme. Now we have a coding scheme here. This code detects errors of up to how many bits. So we need the minimum hamming distance. So for that we have to calculate the hamming distance of all possible pairs. So that we have to calculate among that which is minimum. So that minimum value minus 1. That many bits error we can detect. So if we calculate, all are resulted in 2. So the dmin value is 2. We can detect up to 1 bit error. Okay, minus 1. Dmin minus 1. Those many bits of errors we can identify using this coding scheme. So this is not suitable for detecting 2-bit error. Only 1-bit error this can detect. Next. So we have several error detection schemes. Simple parity check, 2-dimensional parity check, CRC, cyclic redundancy check, and checksum. So these are popular error detection schemes. Simple parity check, this is the simplest linear block coding method. So k-bit data word, n-bit code word where n equal to k plus 1. So the number of redundant bit is only 1. This is called the parity bit. So this is to make the total number of ones in the code word either even or odd. So if it is even means even parity, odd means odd parity. So now if this is the data word, if we use even parity, even number of ones must be there. So no ones are here. So even. So I'm simply adding 0. When I choose the next data word, I must have even number of ones. Only one is there. So to make it even, I'm adding 1 extra 1. And here also only one is there. So I'm adding extra 1. And here already 2 ones are there. It is already even. So I'm adding 0 with that. So this is how simple parity will work. What is the simple parity code word for the given data? 11011 when odd parity is used. So odd parity means odd number of ones must be there. In this code, 1, 2, 3, 4, even number of ones are there. So the extra 1 I should add. So the code word will become 11011 extra 1. This will be the parity bit. So the code word will be 11011 extra 1. Now, 2-dimensional parity check. So here parity calculated both row wise and column wise. We could see here for this sample data, row parities and column parities. Both are calculated. And we'll be sending the information in this row order to the receiver. Receiver will compute column parity for the complete data and row parity for the complete data. So if he receives all zeros, because already we balanced here. So if the receiver receives all zeros, there is no error. Otherwise, there are some errors. Now, can we detect and correct the error for single bit error in a two-dimensional parity checker? Yes, obviously we can, because so if this bit, only one bit randomly it has been highlighted. If this bit instead of 0 it has been converted to 1, the parity value here also here will get changed. Then I can easily track this bit has been changed. So if it is 1, then I can make it 0. If it is 0, then I can make it 1. So we can detect and correct using 2D parity for single bit error. Correction is also possible. Next method is CRC, cyclic redundancy check. So here data word plus n minus k bits of code, redundant bits is added. So that is sent to the receiver. And it is based on binary division. Dividend is used to divide the data word, and data word plus some initial zeros in place of n minus k redundant bits. That is also called as CRC code. And divisor is chosen like n minus k plus 1. So how many number of redundant bits we are adding? Plus 1 bits divisor. So if divisor size is 4, the zeros we have to add will be 3. And we have to apply binary division. We are not interested in quotient. We are interested in the remainder. So that remainder is the CRC code. That will be added with the data word and sent along to the receiver. Now, so this is how it happens. 1001 is the data word and divisor chosen as 1011. So 3 zeros we are adding. That is one size less than this divisor. And we are calculating the remainder when applying binary division. This remainder is added along with the data word that brings the code word. So this remainder is called as CRC code. CRC code. Now, this is division in CRC decoder. The receiver side, he will take the complete code word and use the same divisor, calculates the binary division. If all zeros resulted in remainder, then the data word is accepted. In case, instead of that, some bits are changed here, received information, and the receiver is using the same divisor and he derives a non-zero value as a reminder. So the data word is discarded. Some error has happened. In CRC, if the divisor size is 5 and the data word size is 6, what is the size of the code word? So code word is generated data word plus CRC code size. CRC code size is based on this. If divisor size is 5 means minus 1, 4. So 6 plus 4 is the total code word size. 10. Now, the fourth dominant method in error detection is checksum. So this checksum can be applied to any length message. So that is the main advantage here. And it is mostly used at network and transport layer. And at the source, the total message is divided into m bit units. That means if 16-bit checksum is used, 16 bits it is arranged. If 32-bit checksum is used, the whole message is arranged in 32 size. And the generator, checksum generator creates one more M bit as the redundant bit, that is called the checksum. So message plus checksum is sent to the receiver. At the destination, the checksum checker creates a new checksum for the whole message plus checksum. If the new checksum is all zeros, the message is accepted. There is no error. Otherwise, the message is discarded because there are some bits that are corrupted. So this is one example. If the text we wanted to send is 4 on and it is a 16-bit checksum. So we are arranging it in 16-bit hexadecimal manner. Normally, binary checksum or hexadecimal checksum is applied. Here, this example shows hexadecimal checksum. So the complete word is arranged like this. Initial checksum is added as all zeros and they will be calculating the sum, normal sum, hexadecimal addition. And we will be having one carry. So that is wrapped here. So we are calculating wrapped sum. So that is added here and the sum is wrapped sum is calculated. For this wrapped sum, we have to take the complement. So complement for binary means we'll convert all zeros into 1 and all ones into 0. For hexadecimal, from the maximum value, we have to subtract it. Okay, so the same is for binary also. There the maximum value is 1, so we are subtracting it from 1. Here we should subtract it from 15, that is the maximum digit in hexadecimal. So 15 minus 7, 8, 15 minus C. C is what? 10, 11, 12, 12. So 15 minus 12 is 3, 15 minus 15 is 0, 15 minus 8 is 7. So this is sent along with the original data. And the receiver calculates similar checksum and he will be deriving like this. So if we divide everything, F, 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 F. So all these becomes F. Okay, so here all should come as F. This is not 8F C7 because erroneously this has been replaced. Okay, but here if I calculate sum, all F will come here. So for all F, if I take complement, that is subtracting from the maximum value, I will get all zeros. So the received data is accepted. Now calculate the 16-bit checksum for the data word 1234 1123. 0x means it is in hexadecimal. So now 16-bit checksum means each hexadecimal digit is 4 bits. So first 4, then next 4. So if we arrange in this order, it is actually A. So this is A123. So that we have to correct it. Okay. So in the solution, it has been given correctly. Now we have to perform hexadecimal addition and we'll be getting this value. 7, 5, 3 and here we'll have 11. So 1 and another one we can make it here. Okay, this is wrapped sum. Now again we have to calculate the sum. This will come as 1358. Now I have to calculate the complement. Subtract it from the maximum value 15. So when I subtract it, I'll get ECA7. So this is the 16-bit checksum for the given data ECA7. So this is the final answer. So now in this, we have seen the basics about error detection techniques. Thank you.